We're going to talk about the motion of a charged particle in a uniform magnetic field. And this is a very cool result. And it's not very difficult. We will define a couple of things that sound complicated but aren't really that bad at all. So first, let's review. What do we mean by? Let's review. Okay, the magnetic force, and then well, we know that the magnetic force on a moving charged particle. Now, again, this is not a current. Well, it's a current, but it's a single charged particle moving through space. Now, yeah, right, that's really not a current, because a current you think of as a whole, like a stream of charges flowing through, a wire. But this is a single charged particle that's moving within a magnetic field, and we know that the equation that describes its motion is, or that describes the force on the object because it's moving, is this. The magnetic force is equal to the charge on our particle times the velocity crossed with the magnetic field. So let's take a look at this. A simple case. Let's show a magnetic field, and we'll show it going into the board or into the paper like this. So this means I have a uniform field, and it's just into the paper like this. Okay, and we'll just say that this field extends in all directions forever. And then what we're going to do is we're going to shoot a charged particle into it. So here's a charged, it could be a proton or some positively charged ion. And we're going to shoot it into this magnetic field with an initial velocity of v. Okay. Like that. V. Now, what's the force on this object? Well, the force on the object is, QV cross B. But let's do V cross B using the right-hand rule. So we got V cross B. Okay, fold your fingers into the paper, look at your thumb, and remember, it's going to be the force is going to be perpendicular to the velocity and the magnetic field. It has to be perpendicular to everything. Okay, so here's my force acting on it. So there's my force. Now, let's take a look at this. Do you see this force? Do you see how it's not going to change my speed? It's just going to change it's perpendicular to my velocity vector. Now, what kind of forces are perpendicular to the velocity vectors? Okay, well, just think about what's going to happen here. It's obviously going to change the velocity, going to change the direction of it. So now it's over here, and now it's going to kind of move like this. So there's my velocity vector. And I go V cross B, and now it's going to be like this. There's my force, like that. And then it's going to, be over here, and I got V cross, with the velocity like this. Same velocity, V cross B. Oh, it looks like that, doesn't it? I think you can see what's happening here. Can you? Despite my lousy drawing? Okay. The force is staying constant. And the force is always perpendicular to the direction of my motion. So all the force can do, it can't speed up or slow down my charged particle, but it can change the direction of it at a constant rate. And when that happens, oh, that's terrible. It's going to move in a circle. So if you think about this, the force vector, that circle should be a lot bigger, huh? Because if I extend these, here's my center, and so it's going to be way up there like that. My object's going to move in a circle. The charged particle is going to move in a circle. Now we know what kind of QV, let's see, equals QV cross B. What kind of forces make things move in a circle? Centripetal forces. That's going to be Q, or I'm sorry. And what is the equation for centripetal force? mv squared over r. Right? Now this was a vector, and so this is. Let's just deal with the magnitude of this for right now. We can say the direction of all this is in the negative r hat direction, right, towards the center of the circle. Oh, well, we can, rather than do that, I'll just put negative r hat. Yeah, there you go. So now let's assume that our velocity is perpendicular to our magnetic field right now, and so I don't have to worry about the cross product with the sine theta or anything like that. So let's just say, well, the magnitude of the force is QVB. And this is going to be mv squared over r. So this is the magnetic force is equal to centripetal force. And you can stop here. We could stop right here and just say, okay, all the problems that we're going to have, you can pretty much solve it using this, except of course we could make it look a lot prettier. We could solve it for whatever we want. Now, the book solves it for r. I can do that. So r is equal, well, notice that this velocity cancels this. And if you want to know, okay, and this is a useful thing to ask. If you shoot a moving charged particle into a uniform magnetic field, it's going to move in a circle. So what's the radius of that circle? Well, if you know the charge, it's going to be, and you know the mass, it's going to be, what is it, mv over qb. Right, did I do that right? Yeah. Oh, mv. That's the momentum. And that'll be important later on. But this is the radius of the circulating charged particle. Now, I could solve it for v over r. And I'll show you, let's do that. So we can say that, take this, solve it for v over r, and we get qb over m. So the charge times the strength of the magnetic field divided by the mass. Now what is this? It's the speed divided by the radius. What do you get when you get the speed divided by the radius? Well, we're gonna get what we call, well, we get the angular velocity, don't we? We get the angular velocity, which we call omega, is equal to qb over m. And from this we can figure out all kinds of things. We can figure out the period, how long does it take to go around once. If I, this is in radians per second, I can figure out the frequency, how many complete circles or does it make, per second. I can figure all kinds of stuff out. But this right here has a name, and it has a fancy name, and it's called the Cyclotron Frequency. And there's a lot of history here, and I don't have time to go into it, but the first cyclotrons were great big circles that we would shoot charged particles in, and we would make them go in a big circle. Maybe you've heard of Fermilab, and which is a great big cyclotron. It's just a device that we shoot charged particles into, and we use magnetic fields to bend their paths, and they go in great big circles, and then we can do all kinds of experiments on them. We can smash particles together and do particle physics. So this idea, how many radians per second is this thing going to go as it goes around its circle? It has a name, cyclotron frequency. But it's really just how many, angular velocity of our particle that's moving. Now, the last thing I want to talk about is what happens if the velocity of this is not perpendicular to the magnetic field. Well, first of all, let's take a look at this. This ridiculous situation. What if I do this and just shoot here's my charged particle. What if the velocity is just into the paper as well? So there's my velocity vector, and here's my magnetic. Well, nothing's going to happen. It has to have a component that is perpendicular in order to move in a circle. But what if I had this? And this is kind of hard to draw, so I'll try drawing this in with some perspective. So here's my X, Y, and Z coming out. What if I've got a B field that's just moving along in the X direction? And what if I shoot a charged particle and give it some velocity like this that has an X component, a Y component, and a Z component? Okay. Well, what's going to happen is the X component part of its velocity is not going to have an effect. But the component of the velocity that is perpendicular to the magnetic field, here's our B field right here, is going to cause a centripetal force. And it's going to spiral like this, but it's going to spiral while it moves along in the X with a constant velocity in the X direction. So basically what's going to happen is it's going to move in a spiral like this in space. Okay? And that's pretty cool. But the X component of its velocity stays constant, while the component in the YZ plane, it'll go in a circle in the YZ plane. And by the way, this is what happens to high-speed charged particles when they hit the Earth. The Earth is a great big magnet. It has a magnetic field, and that magnetic field deflects, just like this. It deflects charged particles and bends their path. And so they either protect the Earth for them, or they direct the charged particles to spiral along magnetic fields, and they give us the aurora borealis. So it's pretty cool stuff. So anyway, that's the motion. This is what the motion of a charged particle in a uniform magnetic field looks like. It'll be, if the velocity is perpendicular to the magnetic field, it'll just move in a circle. And of course, things that move in circles have to be forced to do so by a centripetal force, and the magnetic force is the centripetal force, and we can use that. If all you remember is, oh, the magnetic force is the centripetal force, you can pretty much solve all the problems they're going to give you. But you do need to know that V over R is called the cyclonic frequency. That's the angular velocity of our particles, called the cyclotron frequency. And you'll work some problems where they give you this value. So good luck.